Hi, this video focuses on the formulas of chemical compounds and leads into a new topic about how we can use experimental results to figure out what's in our compound. So this starts off as a bit of a review, and it also corresponds with number 5 on your note sheets that were handed out Friday. And I just want to make sure everyone's clear on sort of what compounds actually symbolize and mean when we look at their formulas. So let's think about methane. So we've got methane here. Carbon, 4 hydrogens, right? That's what our formula tells us. If we have a lot of these methane molecules, we have even more atoms because each molecule is made of 5 atoms. If we have a dozen methanes, we'd have a dozen carbons and 4 dozen hydrogens, right? So when we have a mole of methane molecules, we would have a mole of carbon atoms and 4 moles of hydrogen atoms. A few more sort of examples like this, and I encourage you to pause it and try to fill in these blanks yourself. If we have a mole of sodium chloride, what composes sodium chloride? It's not necessarily atoms that are bonded together covalently. Now we're talking ions. So 1 mole of sodium chloride contains 1 mole of sodium ions, Na+, and 1 mole of chloride ions, Cl-. 1 mole of magnesium chloride contains 1 mole of magnesium ions, and how many moles of chloride ions? 2. 1 mole of O2 molecules, molecular oxygen. Remember our I have no bright and clever friends. This is one of those elements. Each molecule here contains 2 atoms, so a mole of O2 molecules contains 2 moles of oxygen atoms. So that's just a little bit of a review, and this is also a bit of a review too. Calculating molar mass. This is directly related to what we were just kind of walking through in those examples. If we have a compound that's composed of a few elements, we need to add all of those molar masses together, and you guys have done that. So just for example, for O2, that diatomic molecule, molecular oxygen, we have to take oxygen's molar mass and multiply it by 2 to get 32 grams per mole. But let's take this one step further, and we did a couple problems like this, but they weren't on the last test. What if we try to identify how many moles of each element we have in a compound? The calculation is a little bit different. And we can do mass mole number calculations for the compound. And if we say have so many grams of compound, we can divide by the molar mass to get moles. We can multiply by Avogadro's number, and that's going to get us molecules. If we need to figure out how many atoms of an element we have, an individual element within the compound, then we need to look at the molar ratio of how many, say, nitrogens there are in a molecule or a formula unit of, say, ammonium nitrate. So that molar ratio can be used as a conversion factor, and it's really best to just look at this in the form of an example. So ammonium nitrate, NH4NO3. It's a fertilizer, and so we've got a practice question here. If you're feeling confident, go ahead and try it without my explanation. If not, I'll work through it. So the question is, how many moles of nitrogen atoms are present in a 1 pound bag of fertilizer? Pounds are not used very often in chemistry, so we have a conversion factor here to get us from pounds to grams. And then second question, how many nitrogen atoms is this? So let's do a little bit of math here. We are intending here to get from the mass of the compound, the mass of ammonium nitrate, to moles of that substance. And then rather than getting our molecules of ammonium nitrate, what we're going to do is focus on the nitrogen. So how many atoms of nitrogen are in every one molecule here? There's 1 there and 1 there, so there's 2, right? So however many moles of the compound we have, we'll have twice as many moles of nitrogen. So a few more things we need besides this pound to grams conversion. We also need the molar mass of ammonium nitrate. And this should be old hat by now. We're going to multiply the nitrogen by 2 because there's those 2 there, plus 4 times hydrogen, plus 3 times oxygen for a molar mass of 80.6. So let's work it out. We start out with 1 pound of the fertilizer. And yeah, we first need to get that to grams. Pounds are not very useful. So I'm going to set up my conversion factor here with pounds on the bottom so that they cancel out. And 453.6 grams are equal to 1 pound, according to the information that was given to me. And so this will give us our mass of the compound in grams. To get to moles, we need to divide by that molar mass, and that's evidenced too by the setup in the conversion factor. We want grams on the bottom, so 80.06, and that dividing by that will get us to moles. So now here's the thing. We've got moles of ammonium nitrate. We're interested in this question in moles of atoms of nitrogen. So we want a ratio of moles. How many moles of ammonium nitrate are there per every mole of nitrogen? And since this conversion factor got us to moles of ammonium nitrate, I'm going to put ammonium nitrate on the bottom. And for every 1 mole of that, there's 2 moles of nitrogen. So this calculation, multiplying everything on top divided by everything on the bottom, gets us 11.33 moles of nitrogen. And that answers the first question. And then, so I've figured out how many moles of nitrogen I have here. The question did also ask about atoms, and now that I know how I have moles of nitrogen, that last step is an easy one. It's one that you've done a lot of times now. If I have that many moles of nitrogen, 11.33, a mole of anything is 6.022 times 10 to the 23rd. And I just need to be careful that I'm applying Avogadro's number to the right thing. I need to make sure I'm multiplying it by the moles of nitrogen and not the moles of the compound. And when I do that, I get a value of 6.82 times 10 to the 24th. With significant figures, we were given 3 on the given piece of information, so we would want to not show that last 3. So that's kind of a warm-up exercise for what we're getting into, which is kind of the same calculation in reverse. A lot of times in chemistry, we have experimental data, and there's lots of instruments in the lab that can tell us what mass of elements are in an unknown sample. And this is usually referred to as mass percent composition. So let's talk about what that really means. The mass percent composition is the mass of each element in the compound divided by the total mass of the compound. And so you can look at a compound's formula and calculate a theoretical mass using the molar masses. And this works because we know that if we have 1 mole of water, for example, it's got a total mass of 18.02 grams, and 16 of those grams comes from oxygen. So this gives us a mass percent composition of oxygen of 88.81%. And then the hydrogen ends up being 11.19%. These should add up to 100% since these are the only 2 elements in water. More often, though, we have some sort of experimental results that tell us something about an unknown compound. So let's say we have some unknown compound. It's 40% this, 30% that, 30% something else. I can do math. So how do we take that information and figure out the formula of that compound? What we want to do is assume that those percentages apply to a specific sample, and using a 100-gram sample works really well. It's a nice convenient number. So if we take, say, the 40% of X and convert that to 40, or express that as 40 grams, we can divide by the molar mass to figure out how many moles are in that arbitrary 100-gram sample. We then take each of those molar amounts and divide by the smallest number of moles. This keeps the ratio the same, but just sort of brings the molar amounts up to sort of numbers that are closer to integers, because eventually we want a formula with integers in it, not with 1.36 as a subscript in the formula. But still, if after you've done that step in number 2, you don't have integers, you can multiply through by a factor that should be pretty apparent to get whole numbers, integers. And this gives us what's called the empirical formula. So this doesn't make a lot of sense just looking at the steps. Easier to look at an example. So let's look at a pharmaceutical. It says here we have ibuprofen. We don't even need to know that necessarily. Let's pretend that we don't know what it is. But an analysis shows that there's 3 elements that make up this unknown compound: carbon, hydrogen, and oxygen at those various percentages. So according to that strategy that I presented on the previous slide, what we're going to do is assume that we have a 100-gram sample. If we did, we'd have 75.7 grams of carbon, 15, or let's start going in order here, 8.8 grams of hydrogen, and 15.5 grams of oxygen. So there's plenty of devices in the lab that can kind of tell us what elements are present in different samples. So the next step in that strategy is that we're going to divide by the molar mass and translate these mass amounts into moles, because if we know how many moles are in the compound, that is the formula of the compound. That formula, as we were saying in the earlier slides, shows how many moles there are of carbon, hydrogen, and oxygen. So yeah, we're going to divide by the molar mass of each of these compounds. And when we do that, we get molar amounts. And go ahead and jump ahead of me if you can. This will give us 6.3 grams. So 6.303. I'm going to retain a bunch of significant figures here. If you round too much, when you start trying to figure out what the integers are, you might be off if you're rounding 6.3 down to 6, for example. Hydrogen is a very light element, so its molar mass is only 1.01. So even though we only had 8 grams, we actually have kind of a lot of moles, 8.7 moles. And then oxygen is a heavier one, so here we only have less than 1 mole of oxygen. So these molar amounts represent the ratio in the compound, but we want to get them to be whole numbers. So the way we're going to do that is divide them all by the smallest number. And this is just kind of a math trick to sort of normalize these numbers, make them look like integers, because if we divide the 0.969 by itself, we're going to get 1. So when we do that for all of them, of course the oxygen turns into a 1. The 8.7 number, when I divide that by the 0.96, that turns into a 9. And then 6.3, when I divide that, it turns into 6.5. So I now am pretty close to integers. I'm not quite there because I can't have a subscript of 6.5 in my formula. But if I now multiply these all by 2, again, I'm preserving that ratio, but I'll have whole numbers. My 6.5 will turn to 13, my 9 to 18, and my 1 to a 2. So this is called the empirical formula, when we have determined the formula of a compound based on weights that we've measured, or in this case that were given to us. Now the thing is, with molecular compounds, if I have C13H18O2, or if I have C26H36, did that right, O4, those are 2 different compounds. And it's okay for molecular compounds not to be in that simplest ratio. So this may not be the molecular formula of this compound, but I have been given a little bit more information here. That overall, this compound's molar mass is less than 210 grams per mole. And if you add this up, you'll see that the molecular mass here, the molar mass here, is 206.3 grams per mole. So we know we can't get any simpler than 13 to 18 to 2. We could get a ratio with bigger numbers, but that would make the molar mass way bigger. So this empirical formula is its molecular formula. Sometimes that may not be the case, that the empirical formula is the molecular formula. And if that's the case, you might be given information like in this practice problem here. Say we know the empirical formula of a sugar, and we know that that empirical formula is CH2O. That's the ratio, 1 to 2 to 1. And we've also done sort of mass spectrometry to know that the molecular mass is 180.1572 grams per mole. So the question is, what's the molecular formula? So to solve that, what we're going to do is add up the molar mass of the empirical formula. And you guys know how to do that. If we end up doing 12 plus 2 times 1 plus 16, we get a molar mass of 30, and if we take a few extra significant figures, 30.03 grams per mole. So this compound's actual molecular mass is 180.16 grams per mole. And we've just calculated the empirical molar mass to be 30.03. This simplifies to pretty close to 6. And so this n is the multiplier that we're going to apply to each of the numbers in the ratio. So really, this compound, which has the ratio of 1 carbon for every 2 hydrogens for every 1 oxygen, the actual molecular formula is 6 carbons for 12 hydrogens for 6 oxygens. So I just did 1 times 6, 2 times 6, and 1 times 6. So that's how you take experimental data and figure out what kind of compound you have. Thanks for watching.